Okay, in what follows, we're going to continue with chapter 3, data models. This is a very important chapter because in this chapter, we're going to discuss a whole series of data models that will allow us to capture the information needs within a particular field, within a particular universe of discourse, as we referred to it earlier on. Here you can find the overview of the chapter. First, we're going to zoom into some of the basic concepts regarding data modeling. We're going to discuss why we need a data model and what are the different steps in designing a data model. Then, we're going to give you a chronological overview of the different data models that have been developed through the past couple of years. We're going to talk about the hierarchical model first, which is an outdated model. We also refer to that as a legacy model. Then we're going to zoom into the CODASYL model, which is also a legacy. So why do we discuss both of these outdated legacy models? Is because many of the IT systems which are still being used nowadays still rely on some of these outdated database technologies. So it is important to be aware of some of the basic concepts and of course limitations of these technologies in order to work in today's database environment. Then we're going to zoom into some of the more popular data models. The first data model that we're going to discuss is the entity relationship model, the ER model. And then we're going to discuss the enhanced entity relationship model, which is basically the ER model with some modeling enhancements added to it. And then we're going to zoom into the relational model, and finally we're going to discuss the UML model. UML stands for Unified Modeling Language. But first, let's discuss why we do data modeling. Well, the reason we do data modeling is because we want to capture the information needs within a particular problem field, within a particular universe of discourse. That could be like a purchase administration system, could be a personnel administration system, could be a university administration system. So the purpose here is to develop a conceptual scheme that will allow us to capture the specifications of the data that we want to actually model, but also we want to capture the constraints to be represented in the database. We also want to capture all kinds of integrity rules and actually represent that in a conceptual model. The main focus of conceptual data modeling is, in other words, to capture all the semantics and aspects of the universe of discourse as closely as possible without taking into account any implementation-specific issues. So we're not going to look at software implementations whatsoever. We just want to understand the particular problem field we're working in. We just want to understand the universe of discourse as closely as possible. The purpose, this particular purpose is going to require a high-level model, a model which is understandable, which is user-friendly. And when I say understandable, I mean understandable by both the business expert, the person working in the business, as well as the database designer. Right? It needs to be a model that both can agree upon, such that in a later stage of database design, that model can be unambiguously mapped to an implementation model. So we need a high-level model, and a model that is often used for this particular purpose is the ER model. ER stands for Entity Relationship Model. But unfortunately, the ER model was not the first model that was historically developed. Different types of data models have been suggested throughout history. And in what follows, we're going to give you a brief overview of those different models. Here you can see the phases of database design that we're going to run through in this particular course. First, we start from the universe of discourse. That is a problem setting. That could be a purchase system, that could be a personnel administration system, or it could be a student administration system in a university setting. The first thing we need is we need to understand the database requirements. That means we need to thoroughly understand what data needs to be modeled, what are the characteristics of the data, what constraints and what integrity rules needs to be modeled. So that's all part of a requirements collection and analysis step. Purpose of this requirements collection and analysis step is to come up with a conceptual design, a conceptual database scheme, which will typically be in a high-level data model. When we say a high-level data model, we mean a data model that could be understood by both the business user as well as the database designer. It speaks for itself that during the requirement collection and analysis step and the conceptual design step, that we will not take into account any implementation-specific issues. So these are both DBMS independent steps. We're only interested in understanding the problem field, understanding the universe of the scores and mapping it to a conceptual model. A conceptual model which both the business user and the database designer can agree upon. And once we have that, we can work towards the implementation. And we can take the conceptual design and map it to a logical design, right? That's typically done using a data model mapping. So you can map an ER model to a relational model, for example. A relational model is going to sit a little bit closer towards the actual implementation. So a logical model is basically already formulated in the data model of the specific DBMS that we are going to use for the actual implementation. So here we're getting closer and closer to the implementation, and of course the final step is to take that logical design, that logical scheme, and map it to a physical scheme during a physical design phase. So there we're actually going to come up with an internal scheme which is going to specify the physical implementation of our database. And these are typically the steps you're going to run through. Very important to remember is that you start off with a conceptual design, which is DBMS independent, and then you get closer and closer to the actual implementation by mapping the conceptual design to a logical design, and then finally to a physical design. Okay, let's now have a look at some of the models that can be used to model information needs, to model data. The first model is the hierarchical model, and you know, this is a very outdated model, as I mentioned before. It's legacy. It was developed in the late 60s by IBM during the Apollo project. So during the Apollo project, lots of information needed to be stored, and the NASA wanted some kind of database management system to appropriately store the information, and of course also to appropriately query all the information, such that the NASA could very easily ask for all kinds of queries relating to the project. IBM developed a hierarchical model and also built a software system that nicely implements the hierarchical model, and that was the IMS system, stands for Information Management System. That was developed end of the 60s, as you see it right there. It was developed in an ad hoc way, so that means there's no original or formal description of that model available. We only have the software implementation. So that means it has lots of structural limitations, and it's part of legacy. It's old software. So remember, the reason why we discuss it is because nowadays, in today's business environment, you can still find some implementations of the hierarchical model around. So as you work in this environment, it is very important to be at least aware of what the model assumes, how it works, and what its limitations are. The hierarchical model makes use of a couple of modeling concepts. First of all, a record type. A record type is a set of records describing similar entities. So you can have a record type student. That's a set of records, a set of students that describe similar entities. So you have the difference between a record, which is an individual student, John Adam, Michael Johnson, those are individual students. And you have a record type, which is gonna represent the collection of students with their general characteristics. Of course, we're going to model in terms of record types. We're not going to look at individual records. As we build our data model, the data model will be built at the level of the record type. So a record type is a set of records describing similar entities, and it's going to have 0, 1 or more records, and it's going to have fields and data items. For students, that could be student number, student name, birth date, gender, email address, and so on. These are what we refer to as fields or data items. Record types can be connected. Imagine that you would have a record type between student and course. Well, a student can follow courses. A course can actually be followed by students. So you have two record types, student and course, which are connected. Now, these connections are modeled in the hierarchical model using relationship types. And it's going to model relationship types between record types. But unfortunately, the hierarchical model is not very flexible. So it will only allow for one-to-n relationship types, which are what we refer to as parent-child relationship types. And in a moment, we will be given some example about that. The relationship types can be nested. We're going to see some examples of that as well. Every relationship type has a parent record type and has a child record type. The record type can be parent in multiple parent-child relationship types. Vice versa, a record type can only be child in one parent-child relationship type. Well, let us immediately illustrate this with an example. Here you can see two record types connected with a relationship type. Think of the record type above as department. That could be the parent record type, and the child record type could be employee. Both of them are connected by means of relationship type, because in a department you have employees working and employees work in a department. The relationship type is characterized by cardinalities. These are the numbers that you see adjacent to it. So you see on top, you see 1 to 1. So that means that the minimum cardinality is 1 and the maximum cardinality is 1 as well. So remember, employee was the child record type. So that means that an employee works in minimum 1, maximum 1 department. That means exactly 1 department. On the opposite end of the relationship type, you have the cardinalities 0 to n, right? The minimum cardinality is 0, maximum cardinality n. So here, this means that in a department, you have minimum 0, maximum n employees working. That's how you should read it. So a parent record type can have multiple child record types. See my previous slide. Vice versa, a child record type can only have one parent record type. A child cannot have multiple parents. A child record type itself can again be parent in another parent-child relationship type. That way you can build hierarchies of record types, all connected by means of relationship types. The record type that sits at the top of the hierarchy is what we call the root record type. It's the start of the hierarchy. The record type that sits at the bottom of the hierarchy, and it can be multiple record types that sit at the bottom of the hierarchy, or what we refer to as the leaf record types. Very important to be aware of is that in the hierarchical model, only those 4 cardinalities are tolerated. So the cardinalities should be 1 to 1 at the parent record type end, and should be 0 to n at the child record type end. As soon as those cardinalities are different, it can no longer be appropriately enforced in the hierarchical model. Note that these relationship types are often referred to in a short way by means of their maximum cardinalities. So in this particular case, we would refer to this relationship type as a 1 to n relationship type, only referring to the maximum cardinalities. Here you can see a hierarchical diagram, for example. Also, we have department, employee, and project, so we have 3 record types. And remember the maximum cardinality. So at the department end, you will always find 1 to 1. At the employee end, you will find 0 to n. And at the project end, you're going to find 0 to n as well. Each of those record types has data items or fields. So department has department number, department name, department location. Department, in this particular case, is the root of the hierarchy. And it has 2 child record types. And in this very simple example, both employee and project are leaf record types. They sit at the end of the hierarchy. Now, what is not very nice is that all record data need to be retrieved by navigating from the root node of the hierarchical structure to the appropriate child record type. Imagine that we have that example that we had before with department as the parent record type and employee as the child record type. And imagine that you would like to know all employees working in the marketing department. Well, what you have to do in order to solve that query is you have to run through all records of the department record type, which in that particular example is the root of the hierarchy. So you run through all the records. First you have finance, then you have logistics, then you have HR, and then you have marketing. Once you have marketing, you found the record, you go down the relationship type, and you're going to navigate through all the employees that work in the marketing department. So you see, this is basically procedural DML. Remember how we referred to procedural DML in the previous chapter. We said procedural DML is the kind of DML in which you have to explicitly program your query. It is completely as opposed to declarative DML. Declarative DML means that you just declare what you want. SQL is an example of declarative DML, as we will see later on. But here, in this particular case, you do not only have to declare what you want, but also how you're going to solve the query. There's no query optimizer that will solve the query for you. So you have to manually program your query. So this is procedural DML, not a very nice DML, not a very nice way of working with data. There's no straightforward way to model end-to-end and one-to-one relationship types. Those can, however, occur in your real-life setting, in your universe of this course. Okay, here you can see an example. A project can be done by 0 to n employees, let's say, and an employee can work on 0 to n projects. So we have an end-to-end relationship type between project and employee. The way we could solve it in the hierarchical model is by assigning one of those record types as the parent and the other one as the child. So we make project the parent and employee the child. If we work it out this way, you're going to see that this is not a very nice implementation because it creates redundancy. In this particular case, you see that employee 130 is going to work on projects 10, 11, and 12. So that means if we implement the end-to-end relationship type in the hierarchical model in this way, that employee 130 is going to see its information being replicated. It creates redundancy. The redundancy depends upon the amount of information in the employee record type, so the number of data fields there, and also it depends upon how many projects on average an employee is working on. So if an employee on average works on a lot of projects, you're going to see lots of redundancy occurring here. Also, if there would be data items or information fields related to the particular relationship type, like the number of hours an employee worked on a project, you would have to store it in the employee child record type. So you see, modeling end-to-end relationship types in this way is not very nice because it creates redundancy, waste of storage space. Another way of modeling end-to-end relationship types in the hierarchical model is by using the idea of virtual child record types and virtual parent-child relationship types. What we do here is the following. We have an end-to-end relationship type between project and employee. So we're going to create virtual child record types. And a virtual child record type contains virtual children with pointers. They only have pointers to a particular virtual parent. So you can see project 10 has 3 virtual children, which refer to employee 130, 131, 145, since these are the employees working on project 10. Basically, those virtual children just contain pointers, references to memory addresses referring the virtual parents. So there's no longer redundancy here, because employee 130 is only stored once, likewise for employee 131. If there would again be an attribute type or a data item that comes with the relationship type, like the number of hours an employee worked on a project, you would store it in those virtual children. This is one way of dealing with the redundancy of modeling end-to-end relationship types in the hierarchical model, but it's not a very nice way because we have to include a virtual construct, the virtual child, which for an end user is not very easy to understand. It is very abstract. What if you have some of the other relationship types? Well, if you have a one-to-one relationship type, this is basically a special case of the one-to-n relationship type whereby n equals 1. There's no natural way of enforcing this in the hierarchical model. So if you want to model a one-to-n relationship type in the hierarchical model, you have to enforce the cardinality in the application programs, in the C or COBOL programs. These are typical examples of application languages that have often been used to work with hierarchical databases. So the cardinality cannot be enforced in the model, only in the application programs. What if you have relationship types of degree 2? Well, here in this example, we only had relationship types of degree 2, right? So we had project and employee, only 2 participating record types. The example I gave with department and employee, only 2 participating record types. But you can also have, as we will see later on quite extensively, you can also have relationship types with degree 3. Well, that is not easy to implement in the hierarchical model. What if you would have relationship types with degree 1? That means whereby you only have one record type that has a relationship type with itself. Later on, we're going to see an example of that, of employee that has a relationship with itself to basically model what employee is supervising what other employee. Well, for those recursive relationship types of degree 1, we need to implement them again using a virtual child record type, which is not very nice. The maximum and minimum cardinality from child to parent equals 1. That means a child cannot exist without a parent. That means if you delete a parent, that you're going to delete all the children that are connected to it. So if you delete the marketing department, you're going to automatically delete all employees that work in the marketing department. This is an effect that we often refer to on delete cascade. It means that the delete is going to cascade throughout the entire database such that you end up not deleting only one record, but in fact, you end up deleting multiple records. Here you can see an example of a hierarchical model for a personnel administration database. You can see we have different record types here. We have a department record type, we have a project record type, we have an employee record type, and basically you can see that the record types are organized into 2 hierarchical structures, hierarchical structure to the left and hierarchical structure to the right, which are both connected using virtual child, virtual parent relationship types. So to the left, you have a department. A department can work on 0 to n projects. Vice versa, a project is being assigned to minimum 1, maximum 1 department. Department has a virtual child record type managed, which is going to basically indicate what employee manages a particular department. You can see that the managed virtual child record type points to an employee record. Department also has works at as a virtual child record type, to basically indicate what employee works at what department. Below project, you will see the works on virtual child record type to know what employee works on what project. So this is a virtual child which is needed to implement the end-to-end relationship type between project and employee. You also see that in the works on virtual child record type, you have worked, and this is going to represent the number of hours that an employee worked on a particular project. Employee also has a manages virtual child, which is basically containing references to employee itself. This is basically to model the hierarchical responsibilities of employees and to see what employee is managing what other employee. This is an example of a data model, which is of course far from perfect. It will contain some limitations, and let us just list some. You will see, for example, that we cannot model that a department has exactly one manager. So if you look at the relationship type between department and managed, right, the managed virtual child record type, at the end of the managed virtual child record type, the cardinalities are 0 to n, which means that a department can be managed by multiple employees. So stating or modeling that department has only one or exactly one manager cannot be enforced here in the model. It's a limitation. Another limitation is that we cannot model that a department has at least one employee. According to the model, you can have departments that have 0 employees, right? Because remember, the cardinalities from department to works at are 0 to n. So you can have departments with 0 employees. Remember, the works on virtual child record type is going to model the end-to-end relationship type between project and employee, and the manager's virtual child record type models a recursive relationship type. Okay, here you can see those limitations that we just clarified, listed again. A next data model that we're going to discuss is the CODASYL model. It has a bit of an ugly name, but it was developed by the database task group of the conference on data system languages during about the same time frame as the hierarchical model. The original model as it was developed by that task group, was a network model. And it had all kinds of popular software implementations like IDMS and CA-IDMS. The original model was a network model, and it had record types and links, and it allowed for one-to-one, one-to-n, and n-to-m relationship types, which was very nice. But unfortunately, not all of this got implemented, and the CODASYL model, which is a specific variant or implementation of the network model, only implemented record types, set types, and one-to-n relationship types. So you can see this is very similar to the hierarchical model, although there are some subtle differences which we're going to clarify in a moment. But you see also there are one-to-n relationship types. Again, the CODASYL model is legacy. It's outdated. It has lots of structural limitations which we are going to explain in what follows. The basic building blocks are record types and set types. Well, record types, we also had that in the hierarchical model. So what's the difference? Well, record type is a set of records describing similar entities, just as in the hierarchical model. It has 0, 1, or more records or record occurrences. It consists out of data items. Well, this is all very similar to the hierarchical model. So we have a record type student that has data items, for example. Now, those data items can be vectors or repeated groups. Well, that's the first important difference. A vector, think of a vector in a mathematical way, is a series of similar data elements. A vector in a mathematical way can have a vector of integers, you can have a vector of real valued numbers. They're actually all elements that belong to a similar type. Well, here as well, a vector is an atomic data item for which a record can have multiple values. It's what we call a simple multi-valued attribute type. Think about a person having multiple email addresses, for example. Well, that you can nicely model by means of a vector. Or a person having multiple diplomas. That you can also nicely model with a vector. A repeated group is a multi-valued composite attribute type. That means it's a composite data item or attribute type that could be meaningfully decomposed. Address is an example of a composite attribute type. Address can be decomposed into street name, street number, zip code, city, and country. And it could also be multi-valued. Remember, students can have multiple addresses. They can have an address here in Leuven, and they can have an address in their hometown or country of birth. So we can model that using repeated groups. It's a multi-valued composite attribute type. So repeated groups and vectors already allow us some more flexibility to model the universe of discourse than the hierarchical model. A set type is the equivalent of a parent-child relationship type in the hierarchical model. And it's also a one-to-n relationship type between two record types. So very similar to the hierarchical model, although there are some differences. We're going to clarify that in a moment. The parent record type, we're going to refer to it here as the owner record type. And the child record type, we're going to refer to that as the member record type. And then we have a set occurrence for each record occurrence of the owner record type together with all the members. That could be 0, 1, or more member records. In a moment, we're going to give you some examples for that. So you can have, for example, a set type between department and employee, and then you have a set occurrence for every department, marketing, HR, logistics, together with all the members, all the employees that work in that particular department. If you contrast that to a pure mathematical definition of a set, a pure mathematical definition of a set says that in a set there's no order and all elements are similar. Well, here, not all elements are similar because you have a department element and you have then employee elements. You have marketing with all the employees, you have finance with all the employees. This basically constitutes one CODASYL set, but it has different members, so it's not according to the strict mathematical rules of implementing a set. So there are different elements, and as we will be implementing CODASYL sets, the members will also can also be ordered. You can say, look, I have my marketing owner record, and then I want to order all the members, all the employees alphabetically, or in terms of their age, based upon birth date. You can physically order them, and the reason you would do that is because that could speed up implementation, for example. So ordering is again something that is available in a CODASYL set, but it's something that is not there when you talk about mathematical sets. You can see the set type cardinalities, and we can do the same example again as we used before. So we had department and employee. So in a department, you can have 0 to n employees working. This is exactly the same as with a hierarchical parent-child relationship type. So in a department, minimum 0, maximum n employees. Vice versa, an employee works in minimum 0, maximum 1 department. The only thing that has changed now versus the hierarchical model is that we will allow this minimum cardinality to be 0. So you can have employees working in 0 departments, for example. Employees that start, for example, in a company and that you just want to have them run through the different departments, and after a while you want to assign them to a fixed department. So there could be employees that are assigned to 0 departments. So this 0 is a first difference here between the CODASYL and the hierarchical model. Here you can see the differences again listed. So a record type can be member record type in multiple set types. So a member record type can have multiple owner record types. In the hierarchical model, a child record type can only have one parent record type. So by having record types be members in multiple set types, we can create network structures, simple networks. Between two record types, if you want, you can also model multiple set types because of extra semantics that you want to capture. Members can also be completely disconnected from their owner. In the hierarchical model, this was not the case. Children cannot be completely disconnected from their parents. Here, this is allowed since the minimum cardinality is 0. One more thing is, of course, related to the data items. As we said before, in the CODASYL model, those data items can be vectors or repeated groups. This was not the case in the hierarchical model. So there are some differences between the CODASYL and the hierarchical model, and the CODASYL model does offer some more modeling expressiveness than the hierarchical model. CODASYL models are always represented as Bachmann diagrams. Charles Bachmann was one of the first to write down the model, so came up with the Bachmann diagrams. So here you can see department in a set type with project, and you can see department in a set type with employee. The set type with employee is going to model in what department an employee works. So a department can have 0 to n employees working in it. Vice versa, an employee works in minimum 1, maximum 1 department. Likewise, on the other end, a department can be in charge of 0 to n projects. Vice versa, a project is always assigned to minimum 0, maximum 1 department. What are some of the structural limitations of the CODASYL model? Well, the first one is that the one-to-one relationship types have to be enforced or modeled in the application programs. This is similar to the hierarchical model. So if you have a one-to-one relationship type, imagine that you have a relationship type between student and master project. A student has to do minimum 1, maximum 1 master project. A master project can be done by, let's say, minimum 0, maximum 1 students. Then you have a one-to-one relationship type, which is again a special case of a 1-to-n, with n equaling 1. Well, this cannot be modeled in a straightforward way in the CODASYL model. So if these are the cardinalities that apply, then we have to manually enforce them in our application programs. C, COBOL, or maybe even Java. If we have n-to-m relationship types, it's also going to present a problem because a member record can only belong to one occurrence of a specific set. So we cannot just define a set type between the corresponding record types. How are we going to do it? Well, we're going to do it using a dummy record type. We're going to include a dummy record type to model the n-to-m relationship type. So remember, again, the same example we had earlier between employee and project. So an employee can work on minimum 0, maximum n projects. Vice versa, a project is being done by minimum 0, maximum n employees. So we have an n-to-m relationship type, or set type in this particular case, between employee and project. And the way we're going to model that is by including the works on dummy. So from employee to works on, we have a set type. We have a set type from project to works on. We're going to have to navigate those two set types, left to right or right to left, depending upon what we want. Here you can see that basically those set types, again, being visualized in terms of individual occurrence at the bottom half of my slide. So you can see employee 130 is going to work on project 10. And then you can follow the linked list, he or she is gonna work on project 11 and project 12. If there would be attributes that come with the relationship type, like number of hours worked, well, number of hours worked can also be stored in the works on dummy record type. But you see, this dummy record type is again not a very nice construct, because it's a construct that we have to introduce in order to deal with the shortcoming of the model, which is not very nice. So for an end user, this works on dummy record type is really not very nice. Also, in CODASYL, we're going to have procedural DML, remember. So suppose a query asks for all projects an employee is working on. So the first thing you have to do is select a particular employee in the employee record type, then navigate through the set type employee project to find all the works on dummy records. And then once you found those works on dummy records, you need to look at the parents or the members, or the owners, I mean, in the project record type. So you're navigating left to right by first positioning on an employee, going down to the works on records, and then finding the projects connected with them. That will allow you to see what projects an employee is working on. If you want to see what employees are working on a particular project, that means that you're going to have to select a project record first. You're going to navigate down, find all the works on members that are connected to it, and then find all the owners of each of those members in the employee project set type. So it's basically, again, a not very nice example of procedural DML. But I told you, CODASYL is still very popular these days, so you can still find a lot of database applications which are basically based upon this CODASYL database paradigm. So procedural DML, not very nice. You can see those implications also listed right here. So other structural limitations of the CODASYL model is that it does not allow recursive set types. So if you have a set type which is going to model the hierarchical responsibilities of employees, there you have only one record type, employee. You again have to define a dummy record, and the dummy record type is then defined as a member in two set types, each having as owner record type the record type of the recursive relationship. And it will require extensive navigation, extensive procedural DML to navigate from one record to another. No relationship types with degree bigger than 2. If you have ternary relationship type, we're going to see some examples of that. There's no relationship types that can actually support that in the CODASYL model. The member records can be logically ordered. That I already told you, right? So if you have member records in a set type between department and employee, for example, you can order the employee records based upon surname, alphabetically, based upon salary if you would want, based upon birth date if you would want. And the way you're going to order them depends upon your applications. If it turns out that you're often going to query employees based upon their surname, then you may want to order them alphabetically, because that could speed up your applications, because then your applications no longer have to take care of the sorting themselves. That could be very useful for data manipulation. If you have the root member record type, so that's the record type that sits at the top of the hierarchy, for example, department, the system can then act as the owner of that department record type, and then you have a singular or system-owned set type. That means that you have a set type in which you only have one set occurrence. The set occurrence will be the system, then followed by all those owner records. And again, those owner records can be sorted. You could again sort departments based upon their first letter alphabetically, for example. That's a singular set type. It contains only one set occurrence, and it's meant to be the set type for the root record type sitting at the top of the hierarchy. Here you can again see the personnel administration example, but now visualized in terms of the CODASYL model. So we have an employee record type, a department, and a project record type. Those are the most important record types. Between department and employee, we have a works at set type, which is going to specify at what department a particular employee works. We have a managed set type, which is going to specify what employee manages a particular department. Between department and project, we have in charge of set type, which is going to actually model what department is in charge of what project. Then we have two dummy record types, hierarchy and works on. Well, the works on dummy record type we already clarified earlier on. This is to basically model the end-to-end relationship type between employee and project. And in that works on record type, we also have worked, which is the number of hours a particular employee worked on a project. We also have the hierarchy record type. The hierarchy record type is going to model the recursive set type between employee to model the hierarchical responsibilities of employees. Who is managing who? So here you can see one set type, the first one to the right, which is going to indicate what employee an employee is managed by. The other set type to the left, is going to indicate which employees a particular employee manages. But you see those dummy record types are again not very nice record types, because these are record types that we need to introduce in order to address some of the limitations or shortcomings of the model. So clearly, again, this model is going to have some limitations. The hierarchy record type is introduced to model the hierarchical relationship types, not very nice. The works on record type is introduced to model the end-to-end relationship type between employee and project, not very nice. The model says that an employee can be managed by multiple other employees, right? So here, if you look at the set type between employee and hierarchy, you have a managed by set type. It basically says that an employee can be managed by multiple other employees, which is maybe not what you want. Ideally, you want an employee to be managed by at most one other employee. The model also does not allow to enforce that a department must have exactly one manager, right? So if you look at the set type between department and employee, you have a managed set type, so you can have departments that have 0 managers. The model does not allow to enforce that a department needs to have at minimum at least 1 employee, so you can have departments that have 0 employees according to the model, which is maybe not what you want in a real-life setting. So you see that this model does have a lot of limitations, unfortunately, which you also see listed right here as well. So I basically went through all the limitations as you can see them listed right here. Okay, let's move on with the third data model, which is the entity relationship model. This is a very popular model, and this is going to play a very important role in the remainder of the class. It was formalized and defined somewhat later than the hierarchical CODASYL model in 1976 by Chen. And the main ideas here, or the main concepts, are entity types, attributes, and relationship types. We're going to talk about entity types first, and we're going to define attribute types and key attributes. We're going to talk about weak entity types, which is a very important concept here. We're going to talk about attributes. We're going to talk about simple or atomic attributes versus composite attributes. We're going to talk about single-valued versus multi-valued attributes. We're also going to zoom into relationship types, and you're going to see that in the ER model, we have a lot more flexibility when it comes to relationship types. So we're going to have unary, binary, ternary relationship types. Those will implement all kinds of cardinalities, 1-to-1, 1-to-n, obviously also n-to-1, and n-to-m. So all of that will be supported in the ER model, which is really very neat. We're going to talk about participation constraints, total, partial. Relationship types can have attribute types. We're going to zoom into that as well. The nice thing about the entity relationship model is that it also comes with an ER diagram, which is a very nice, intuitive, user-friendly graphical notation of a conceptual scheme. First, let's talk about entities and attributes. Entities first. Well, an entity is the same as a record. Remember, in the hierarchical and the CODASYL model, a record was an individual occurrence of a record type. As such, an entity is an individual occurrence of an entity type. So it's going to represent a thing or concept in the real world with an independent existence. A particular student, John Adam. A particular faculty member, Bart Baesens. A particular building, this building. A particular university course, database management. This is an entity, an individual occurrence of an entity type. An attribute is an individual occurrence of an attribute type. So it's going to represent some property of interest that further describes an entity. And a particular entity will have a particular value for its attributes, which then are going to be stored in your database application. So that could be a student's name, John Adam, could be a faculty member's birth date, could be a particular building address. So entity types can be instantiated into entities. Attribute types can be instantiated into attributes. Entity types gonna have attribute types. Student entity type has attribute type student number, student name, gender, birth date, email address, etc. Here you can see some examples. So we have a student entity type with an individual student entity. So we have name, Jason Cooper, address, and birth date. We also have a particular address entity type with a name and then the value of the address itself. Naamsestraat 69, 3000, Leuven. These are two individual entities, both being occurrences, individual cases of an entity type. Now the attributes can be, there could be various types. They could be simple, atomic, or composite. They could be single-valued or multi-valued. They can be stored versus derived, or you can also have null values. Let's zoom into that into a little bit more detail. A simple attribute type is an attribute type which is atomic, which cannot be further meaningfully decomposed. A composite attribute type is an attribute type which is composed and which is composable, so we can compose it into subparts. Here you can see an address composite attribute type that can be decomposed into street address, zip code, and city, for example. You can also have multi-valued attribute types. Multi-valued attribute types are attribute types that can take on multiple values, as the name suggests. So here, address could be a multi-valued attribute type because a student can have multiple addresses. Maybe also diplomas. Diplomas can be multi-valued. Maybe also email addresses. A student can have a multi-valued email address attribute type. A derived attribute is an attribute that could be derived from another attribute. If you're going to store the age of people, that would be a very unwise thing to do because the age is going to change on a yearly basis, hopefully. So that's why it's a lot wiser to not store the age, but store the birth date. So you can see the birth date being stored so that the age can be calculated. Well, age then becomes a derived attribute. A null value means a value that is unknown or inapplicable. So here you can see Jason Cooper with a birth date, and imagine that Jason Cooper is still a bit outdated and does not have an email address. Well, then you can see that email equals null. Entity types, keys and domains. An entity type is going to define a collection of entities that have the same attributes and represent similar real-world entities or objects. So you can have the entity type student and individual entities, John Adam, individual students. So the entities are said to be instances or cases of a particular entity type. They're individual occurrences, just as we had records and record types earlier on. A key attribute is an attribute whose values are distinct for each individual entity. Think about student and student number. A student has an individual student number, so student numbers can be used to identify students. They are what we refer to as key attributes. An attribute, such key attributes can then be used to uniquely identify each entity, and that will be very important for physical storage, as we'll see later on, but as well as for implementing relationship types, but that we're going to come back to later on. Note that a key attribute does not need to be a single attribute, like student number. Student number is a single attribute. The key attribute can also be a combination of two attribute types. Think about a flight administration example, and you have two. You have a flight that has a flight number and a departure date. So which one would be the key attribute, flight number or departure date? Well, let's think about it. The first one we consider is flight number. But what is a flight number? Well, a flight number is the number of a flight on a particular date. Imagine that you have British Airways and you have a flight between London and New York, and the flight number is BA25. I'm just making up something. You can have a flight BA25 today, tomorrow, the day after. So you have a flight BA25 every day of the week. So BA25 is no longer uniquely identifying a flight. So what about departure date? Can we use that as our key attribute? Well, on one particular date, you can have multiple flights. So nor flight number nor departure date are sufficient as the key. So what we need to do is we need to take the combination of both flight number and departure date then make up the key. So this is an example of a case in which you have two attributes that together make up the key attribute. The domain is then the same as a data type. So a domain is associated with an attribute, and it's going to specify the set of values that may be assigned to that attribute. So you can have a domain for birth date. Domain could then specify that birth date is typically stored as month or day, month, year. You can have a domain for email address. Email address means that you have a set of characters followed by an @ sign, followed by a set of characters, followed by a dot, and ending in com.be, whatever. So a domain is going to specify the set of admissible values for a particular attribute, and it's typically not represented in an ER model. You can see an ER diagram. So you have a course entity type with course number, which is underlined. The reason it is underlined is because it's the key attribute. Key attributes are always underlined. Then we have student and has student number underlined because it's a key attribute. Address, and you see that it has two circles. Address, that means it's multi-valued. So address is a multi-valued attribute type in this particular case. And then we have name, which can be decomposed into first name, into surname. So name is a composite attribute type because it can be further meaningfully decomposed into first name and surname. Of course, we will also be able to model relationship types between the entity types. So a student can take courses, a course can be followed by students. So we're going to have relationships and relationship types. A relationship type is a collection of relationships. So a relationship is again the individual occurrence of a relationship type, just as we had with entity and entity type. Entity is an individual occurrence of an entity type, while a relationship is going to represent the association between two or more entities. The relationship type is going to then define the set of relationships among instances of two, one maybe, or more than two entity types. Each instance of a relationship type is going to carry a similar semantic meaning. When we model data requirements, of course, we're going to particularly be interested in those relationship types. Here you can see relationship type between student and course. So we have two courses, database management and data mining, and we have a student, Jason Cooper, and Jason Cooper is gonna actually attend both of these courses. So there's a clear relationship between Jason Cooper and both of these courses. The way we're gonna represent relationship types is by means of a diamond. So here you can see the diamond between student and course, and the diamond can be interpreted as two arrows. So there's just two arrows connected to one another, making up the diamond. And then the arrows can be read in both directions, right? So you can read an arrow from student to course, and you can have an arrow from course to student. In order to make your ER diagrams very easy to understand, very easy to read, it makes sense to attach a name or meaning to each relationship type. Well, here the relationship type is called enrolled for, because students can be enrolled for courses, and for courses you can have students enrolled. The degree of relationship type is the number of entity types that participate in it. So previously we had student and course, only two entity types, so the degree was 2, because we have two entity types participating in it. So that's a binary relationship type. You can also have a unary relationship type, so that means a relationship type where you only have one entity type. For example, a recursive relationship type to model hierarchical responsibilities of employees, as we will see in a moment. You can also have ternary relationship types. This is less frequent, but it could occur, and we're going to give an example of it. In case where the same entity type participates more than one times in a relationship type. This is a typical example in a recursive relationship type. You have the same entity type, employee, which is going to participate more than once. Then it makes sense to use role names. Role names are used to distinguish the meaning of each participation and help you to interpret the recursive relationship type. So let's see an example of this. You can have employee. So we have a relationship type, which is unary, since it has only one entity type participating, employee. And relationship type is called supervisors. And an employee can be supervisor of other employees. Vice versa, an employee can be supervisee of a particular employee. So both supervisor and supervisee in the above example are role names. They help you to interpret the relationship type supervises in an unambiguous way. You can also have ternary relationship types, whereby you have 3 entity types participating. So here you can see that tourists can make bookings for a hotel at a particular travel agency, for example. That's a ternary relationship type. Relationship types are going to be characterized using cardinality ratios, and the cardinality ratios are going to specify the minimum or maximum number of relationship instances that an entity can participate in. And again, just as we had with the hierarchical and the CODASYL model, we have a minimum and maximum cardinality. The minimum cardinality can be 0, that you have when an entity can occur without being connected to another entity, partial participation. We mean with that? That means that entities can be sometimes coupled to other entities, other times not, so there's partial participation. You can also have a minimum cardinality of 1. That means that an entity must be connected to at least one other entity, which is total participation or existence dependency. It means that an entity must always be connected to another entity, so it's existent dependent. The existence of that one particular entity depends upon the existence of another entity. That's what we call existence dependency. Maximum cardinality can be 1 if an entity can be connected to at most one other entity, or it can be n when an entity can be connected to at most n other entities. So again, just as with the hierarchical and the CODASYL model, relationship types will be often characterized by means of their maximum cardinalities, and those could be 1 to 1, 1 to n, n to 1, n to m, and so on. You can see some examples, so let's just read them. The top one first. A student can be enrolled for minimum 1, maximum big M courses. For a course, you can have minimum 0, maximum big N students enrolled. A man is married to minimum 0, maximum 1 woman. A woman is married to minimum 0, maximum 1 man. If you read those relationship types, it's always important that you try to read them using the words minimum and maximum, because that will allow you to very easily understand what is being modeled. A project is managed by a minimum 1, maximum 1 employee. Minimum 1, maximum 1 employee, that means exactly 1 employee. An employee is going to manage minimum 0, maximum n projects. Again, relationship types are often referred to by means of their maximum cardinalities. So the first relationship type enrolled for is an n to m relationship type. The second one is a 1 to 1 relationship type, and managed by is an n to 1 relationship type if you want. There exists some alternative notation for relationship types. You can see that this is a notation where people are only going to use the maximum cardinalities, and the minimum cardinalities are going to be reflected by means of double lines. So I'm not a big fan of that, but if you would want to use that modeling notation in the assignment, that's fine by me. Relationship types can have attributes, similar to those of entity types. So if you have an n-to-m relationship type between project and employee, you can have an attribute type, which is going to model the number of hours that an employee worked on a project. If you would have 1-to-1 or 1-to-n relationship types, the attributes can always be migrated to one of the participating entity types. When you have an n-to-m relationship type between project and employee, which is the example I just gave, then the attribute type cannot be shifted to one of the participating entity types, and you have to connect that attribute type to the relationship type itself. It has to be specified as a relationship type attribute. So here you can see a relationship type between student and course. We have an attribute type test score, which is going to give you the score that a particular student obtained for a particular course. Now, since it is an n-to-m relationship type, we cannot just pass on the test score to either course or students, right? Because there could be multiple test scores for a course, there could be multiple test scores for a student. So in order to know the test score, you need to know both the student and the course, and that's why we connect it to the relationship type. Weak entity types are a particular kind of entity types that do not have their own key attributes. They're called weak entity types because they are not powerful enough to come up with their own key attributes. So entities belonging to a weak entity type are identified by being related to an owner entity type. So it will need a key from the owner entity type, which is what we call a partial key. A weak entity type is always existent dependent. And the reason it is existent dependent is because it needs the partial key, or it needs basically the key from the owner entity type. So a weak entity type always implies existence dependency, but vice versa does not go. Existence dependency will not always imply a weak entity type. Example. You can see a hotel administration database with two entity types, hotel and room. A hotel is an entity type that has hotel number as its key attribute. It's underlined, remember, and it also has a name. So every hotel has a unique hotel number. Obviously, a hotel has rooms, so we have a room entity type here as well. And they're connected with a relationship type belongs to. So a room belongs to minimum one, maximum one hotel. That means a room belongs to exactly one hotel. Minimum one, remember existence dependency. A hotel can have 0 rooms. Imagine that you have hotels which are under construction, then we will allow hotels that have 0 rooms, but they can have up to n rooms, obviously. A room has a room number, and you can see that it's partially underlined here because room number is a partial key. Why? Because with room number, we cannot uniquely identify a room. So if you think about room number 25, you can have many hotels that have room number 25. So if you have 5 hotels, you're going to have 5 times a room number 25, assuming that every hotel has at least 25 rooms. So room number can only be used to uniquely identify a room if we also have the hotel number. So room is a weak entity type since it cannot come up with its own key. Room number is insufficient. So in order to come up with a key, room has to borrow hotel number from hotel, and if you put hotel number right there, then hotel number together with room number make up the key of room. Obviously, a weak entity type is always existence dependent. A room should always be connected to a hotel. So you can see the minimum cardinality 1, which indicates the existence dependency in this particular case. Vice versa is not true. So an existence dependent entity type is not weak. Here you can see an example. So we have suppliers and purchase orders, and there's a relationship type. So a purchase order can be outstanding with a particular supplier. So supplier has supplier number as the key attribute type. Purchase order has purchase order number as the key attribute type, and there's a relationship type between them. So a supplier can have minimum 0, maximum n purchase orders outstanding. A purchase order is always connected to minimum 1, maximum 1 supplier. So a purchase order is always connected to exactly 1 supplier. Minimum 1, that means purchase order is existence dependent from supplier. So purchase order is an existence dependent entity type. Is it also weak? Well, it's not weak. Purchase order is not weak because it has its own key attribute, which is purchase order number. Yeah, so purchase order number is a key attribute identifying the purchase order entities. So this is an example of a weak entity, of an existent dependent entity type, purchase order, which is not weak. So this illustrates what we said before. A weak entity type implies existence dependency, but existence dependency does not imply a weak entity type. Let's have another look at relationship types, because most of the relationship types that you're going to see will be binary relationship types. That means that you're going to have 2 entity types participating in them. But it need not be binary. It could be ternary. Assume a problem situation whereby suppliers can supply parts for projects, and a supplier can supply the same part for multiple projects. A part for a project can be supplied by multiple suppliers. A supplier can supply multiple parts for a project. A supplier has a unique name and address. A part has a unique part ID and name. A project has a unique project ID and name. And in the model that we're going to construct, we also need to include the quantity in which parts are supplied for a given project by a given supplier. The way you can model that is by a ternary relationship type. So a ternary relationship type means a relationship type of degree 3. That means you have 3 participating entity types in a relationship type. So the entity types are obviously supplier, project, and part. And let's just read the cardinalities first. And we're going to start by reading the cardinality 0 to n next to project. So next to project, you see 0 to n. What that means is the following. A supplier can supply a part to minimum 0, maximum n projects. Let's then read the cardinalities 0 to n just above the part entity type. A supplier can supply for a particular project minimum 0, maximum n parts. Okay. Let's now finish and read the cardinalities next to supplier, which are also 0 to n. A part for a project can be supplied by minimum 0, maximum n suppliers. Each of them have their key attributes. Supplier has supplier name, project has project idea, part has part idea, and we also have an attribute of relationship type, which is quantity. That's a ternary relationship type. So the question obviously comes like, can we not model this as a series of binary relationship types? If we just make a binary relationship type supplies between supplier and project, a binary relationship types can supply between supplier and part, and a binary relationship type uses between part and project, isn't the problem solved then? It is not, because here, let's say that this is the situation. We have two projects. Project 1 uses a pen and a pencil, and project 2 uses a pen. Supplier Peters is going to supply the pencil for project 1 and the pen for project 2, and Johnson is going to supply the pen for project 1. So here you can see, if you model it in a ternary relationship type, you have the relationship type supply. You see that Peters is going to supply the pencil for project 1, Peters is going to supply the pen for project 2, and Johnson the pen for project 1. Now, if you decompose this ternary relationship type into a set of binary relationship type supplies, uses, and can supply, what are you going to see? Well, first of all, you see that Peters is going to supply to project 1, just as Johnson. So both Peters and Johnson supply to project 1. That's what the supplies relationship tells us. The uses relationship tells us that project 1 is going to need a pencil and a pen, right? Let's focus on the pen for a moment. So project 1 needs a pen. In the can supply relationship, you will see that both Johnson and Peters can supply the pen. So Johnson and Peters, they do supply to project 1. Project 1 needs a pen, and both Johnson and Peters can supply the pen. So I don't know who's supplying the pen to project 1. If I decompose the ternary relationship type into a set of binary relationship types, I'm not going to know who supplies the pen for project 1. Whereas if I keep it as a ternary relationship type, I will know that it's basically Johnson supplying the pen to project 1. So if you decompose the ternary relationship types as binary relationship types, it cannot be seen that Peters does not supply the pen for project 1, and in fact is Johnson supplying it. So we have a loss of semantics when the ternary relationship types are being represented as a set of binary relationship types. Binary relationship types, however, can be used to model additional semantics, as you see right here. So here you can see instructor, semester, and course, 3 entity types with a ternary relationship type between. So an instructor is going to offer a course during 0 to n semesters. A course during a semester can be offered by minimum 1, maximum n instructors, and an instructor during a semester can offer 0 to n courses. Each one with their attribute types and key attributes, but you also see an additional relationship type, can teach, between instructor and course, which is basically going to model additional semantics like what courses an instructor can teach, is qualified for. Okay. Some tools, some modeling tools will not allow you to model ternary relationship types, and a nice workaround is by using weak entity types. So here we have again that supply relationship type, which we can model as a weak entity type. So we're just going to model supply as a weak entity type, and it's going to borrow supplier name from supplier, it's going to borrow part idea from part and project idea from project, and then going to add quantity as an additional attribute type on top of that. So this is one way of representing a ternary relationship type using a set of weak entity types. Here you can see again the example ER model, which we already discussed in the hierarchical model, in the CODASYL model, and now in the ER model. And you're going to see in the ER model that we have a lot more semantics that we can add to the model. So we basically have 3 entity types: employee, department, and project, each with their attribute types. So for employee, that's employee number, name, sex, address, date of birth. You can see employee number is underlined because it's a key attribute. For department, we have department number underlined, it's a key attribute. For project, we have project number underlined, it's the key attribute. First thing that strikes you is that you do not have any dummy entity types here. There's no need for dummy entity types, just as we need it in the hierarchical model or the CODASYL model, we don't have it here. So this model is a lot more user-friendly, it's a lot more transparent, it's a lot more easy to read. Let's have a look at some of the relationship types. First of all, the unary relationship type. An employee is going to manage minimum 0, maximum n other employees. An employee is managed by minimum 0, maximum 1 employee. That's a unary relationship type. We can model that perfectly like that without having to use a dummy record type. Then we have two relationship types between employee and department. So an employee is going to manage minimum 0, maximum 1 department. A department is managed by minimum 1, maximum 1 employee, or exactly 1 employee. Remember, minimum 1 means existent dependent. So in this particular relationship, you see that department is existent dependent from employee. An employee is going to work on minimum 1, maximum 1 department, and in a department you have minimum 1, maximum n employees working. Then you have between department and project. A department is in charge of minimum 0, maximum n projects. A project is assigned to minimum 1, maximum 1 department. That means exactly 1 department. An employee is going to work on minimum 0, maximum n projects, and a project is being worked on by minimum 0, maximum m employees. And you see that the works on relationship type also has worked, which is the number of hours an employee worked on a particular project. This is an ER model. You can see any kind of relationship type is possible: 1 to 1, 1 to n, n to m, and so on. Any kind of minimum cardinality is possible. So you see a lot more flexibility than we had in the hierarchical and CODASYL model. It's a very user-friendly model, and that's why it will often be used to capture the information needs within a particular problem field. However, it does have weaknesses. The first weakness is that the ER model presents you with a temporary snapshot. That means a photo at a given moment in time. That means temporal aspects cannot be very nicely modeled. If we would say, like, look, a project needs to be assigned to a department after 1 month. So after the project is first defined, after 1 month it needs to be assigned to a department. That cannot be nicely modeled here in the ER model. If we say, like, an employee cannot return to a department of which he or she was previously a manager, that's a temporal based rule. That again cannot be very nicely enforced here in this ER model. If we say, look, when a new employee starts, we want to kind of have him or her circulate between different departments, and he or she should be assigned to a department after 6 months. Well, it's again a temporal rule which cannot be nicely modeled. Also, if we have integrity rules that span multiple relationship types, it cannot be very nicely modeled. So here you have, between employee and department, you have two relationship types, and there's an obvious rule that connects both of them. Because obviously, an employee should always work in a department that he or she manages. You cannot have an employee, John Adam, managing marketing and working in finance. Well, according to my ER model, this is perfectly okay. You can have employees that manage marketing and work in finance. That should not be the case. We don't want that. Well, actually, that cannot be enforced in the model. Also, when you look at the three relationship types that connect employee to department, department to project, and employee to projects, and it says that employees should always work on projects assigned to departments to which the employees belong. That's a very obvious rule that cannot be enforced in this ER model. So you can have employees that work on marketing projects, whereas basically the employees work in the finance department. That should not be tolerated. That should not be allowed. Well, according to my ER model, this is perfectly allowed. You can have employees working on marketing projects, whereas the employees are situated in the finance department. It's also not possible to include integrity rules, trigger rules, and or behavior, right? Integrity rule could be like, worked should be a positive integer. Maybe you want to specify a domain for date of birth, or maybe you want to specify a domain for address that has street name, street number, zip code, city, and country. All of that cannot be added to the model. So all of that needs to be appropriately documented if you want to use this model in a real-life environment, and if you want to start developing database applications with this model. Here you can see those limitations again listed. So remember, temporary snapshot, cannot guarantee consistency across multiple relationship types, and not possible to include integrity rules. Here you can see the notation. We covered most of the notation in the section. We've spoken about entity types, weak entity types, relationship types, attributes, key attributes, etc. The ER model is not a perfect model, and there's a very important extension of the ER model, which is the enhanced entity relationship model. The enhanced entity relationship model is basically an extension of the ER model, which is going to offer some additional modeling concepts like specialization, generalization, categorization, and aggregation. But that we will cover in the next section.